right. So my name again is Shira Frank. I'm a strategic advisor with the MIT Digital Currency Initiative and also work on some of our user research that we do collaboratively. I'll just be introducing the agenda before I turn it over to our main presenter, Sam Stuewe. So if we can go to the next slide. Great. So just to orient everyone, if you're anything like me, it's helpful to settle in and relax and start to really learn when you know what's coming. So first, we're going to do a pretty meaty, intensive discussion and presentation with Sam Stuewe, who's the lead maintainer of the OpenCBDC codebase. Sam will give a whirlwind tour of everything that is in that now many code bases. And then we'll take questions from the audience. This will be moderated. So the best way to get your question in is to fill it in at any time through the chat. As I mentioned before, Alex will be moderating that. So ping Alex or ping anyone on the team and we'll make sure it gets into the queue. But specifically ping Alex if you see Alex's name, send in your question and we'll make sure that that Q&A can be really rich and get to as many questions as possible. Then we'll do breakout discussions. Hopefully where a little bit more depth is possible, and we'll also get into specific issues. So we'll do a privacy breakout, a breakout on interoperability. Those will both be more technical in nature. And then we'll have a third breakout, which will be non-technical in nature. It can focus on the project overall, but specifically we'll share some research we've been doing into financial inclusion. Finally, we'll do a quick closing and a call to action, and that will be the agenda. So without further ado, I will hand it over to Sam. Take it away, Sam.
Hey everyone, just a quick technological check for my co-hosts. Can everyone hear me all right?
Sounding great.
Excellent. Hello everyone, I'm Sam Stuewe. I am a CBDC software engineer here at the DCI, and I am the lead maintainer of OpenCBDC. Before I dive into the actual meat of the whirlwind tour, like Shira mentioned, I do want to say very clearly that I'm not speaking on behalf of any of our collaborators at the DCI. Any opinions that are expressed during this presentation, you can think of as mine and mine alone. I don't mean to speak on behalf of anyone. All right, so without further ado, let's go ahead and dive in. So I think it's useful to start from a place of where the DCI's CBDC research has been focused. And our core mission has been to try and cooperatively find really useful and actionable answers to some of the most pressing questions surrounding that mission have been focused on user agency and open collaboration and kind of neutral, rigorous research. So far, our research priorities have been focused particularly on security, scalability, and privacy, but we'll also talk about where some of our priorities are heading in. And for the most part, we go through our research with an approach of neutral and collaborative technology-focused research and development, with a particular focus on surfacing the data necessary for us to know that any potential CBDC design that actually gets deployed will kind of maximize user agency, accessibility, and personal privacy. To give you some idea of where we started, the DCI's original CBDC work started in 2016, but this project really began somewhat unofficially in 2020 with the launch of Project Hamilton, which is the DCI's collaboration with the Federal Reserve Bank of Boston on central banking. In February of this year, the first phase of Project Hamilton's work was released publicly, culminating in the launch of OpenCBDC itself. And since then, we've actually had kind of a busy year. So we've since begun collaborations with the Bank of Canada and Bank of England on CBDC research. We've released a lot of our supporting testing infrastructure and some ancillary repositories around some of our kind of core work. And we've also open sourced some newer designs, things that we're kind of working on currently, including privacy enabling tamper detection, programmability, and our first kind of user-facing wallet. And I'm going to go over a lot of that a little bit more in depth as we go. This is kind of a general overview from where we're starting. Before I get into too much of the meat, it's probably worth taking a moment to ask what is maybe an obvious question. What is CBDC? So traditionally, central bank money is taken two forms. First, in the form of physical cash, physical currency, namely cash, which is kind of widely available for public use, both by individuals like you and me, and also by companies and other institutions and anyone else interested. And then second, digital reserves, which are held really by eligible financial institutions at the central bank. So when we talk about CBDC, we're talking about a third form of central bank money that is digital, much like digital reserves, but more like cash, available for wide use, either directly or through an intermediary. So it's worth mentioning this is kind of a totally new kind of central bank money. OpenCBDC then is our free and open source project focused on exploring all of the potential designs available to CBDCs, what the trade-offs of those designs might be, and what the implications of those are for both the financial system itself and also wider society. Okay, with that kind of maybe obvious but really fundamental question asked and answered, let's kind of take a step back and really talk about what CBDC means or what it could mean. It's worth mentioning that we're talking about a completely new infrastructural layer. CBDC, in some sense, represents an opportunity for a ground-up redesign, far beyond the notion of just providing a new layer for settlement finality and a common data model, which I don't mean to downplay are incredibly important. This is an opportunity for us to really rethink what we have in our current financial system and potentially pull on all of the best aspects of what we have and maybe rethink or fix some of the problems we currently face. So the spectrum of how a CBDC could be designed really runs a whole gamut of options. You might see something far to one side of the spectrum that's a lot closer to the financial system we have now, a little bit more two-tier, where, for example, you need access to a commercial bank account in order to access the system. And you might see something kind of at the total other end of the spectrum, where it takes the form of central bank-backed tokens issued on a public blockchain. The DCI's CBDC research specifically, and OpenCBDC in general in its work, has really been focused more on this middle ground, what we like to call digital cash, which is focused on the notion of taking the kind of best aspects of cash that we have now, for example, really clear expectations and guarantees about how the system works or when finality happens, and making it easy to use, fully private or at least generally private, functional offline, and widely available, and pulling those forward into this new kind of digital space, reproducing the best aspects that we can. And I really do want to just kind of drive home what a ground-up redesign opportunity this is. So, for example, I want to clarify one particular thing. Many people, when they talk about CBDCs, will separate between a retail and a wholesale CBDC. Wholesale CBDC, you can imagine, is taking place a little closer to the left-hand side of this spectrum on the screen, where you have an intermediary layer, and people like you and me would need to have some access through an intermediary to get access to the system. What we're focused on, this notion of digital cash, lies more on the retail side, where it is a direct liability of the central bank still, but how you access the system is direct rather than through any particular. That's not to say that there won't be intermediaries, and we can talk about that more later, but I just want to clarify what the relationship is on how the model would function. So that's the kind of notion of the realm of spectrum for how CBDC might operate. Now let's take a moment and talk about why we actually went this route. So we kind of have taken a somewhat novel approach to this system. In particular, we are largely focused on the free and open source, not just on the software side, but also on the research side and the data science side. So there are many reasons why free and open source is compelling for a lot of people. I'll just kind of go through the three that I find most particularly important. So this kind of enables everyone to be involved. We can leverage the expertise of the greatest minds really around the world. And despite the fact that the DCI is based in Boston, we can really have this research be more globally focused. Second, this is maybe the core ethos of the free and open source movement. There's a notion that the diversity of ideas and contributors breeds an ingenuity of, which is to say, when people have wildly different backgrounds, they bring different contexts to particular problems. That broadens the horizon of potential solutions and usually means possible ways of fixing problems that may not have ever come up before become accessible, and usually leading to better outcomes. And finally, it's also worth mentioning that what we're talking about is a piece of public infrastructure. So having a public review and people actually involved in the process of what is being made forms a vital amount of accountability necessary in any kind of public. So beyond just free and open source, we're clearly very technology focused. And there are a couple of reasons for this, but maybe the most central is that this is a digital system. So the technology and the capabilities of the technology we're capable of building really determines what's feasible and what actually can be done. But this can't only be technology work, and we kind of know that going in. So we're focused on the technology because that's where our expertise lies. When it comes to any new piece of infrastructure, there's a significant benefit in having a feedback loop, particularly between the technology side for feasibility and the policy side focused on outcomes. It's also worth mentioning things like economic incentives and societal implications fit into this feedback loop as well. And that lets us iterate on design and hopefully get to something closer to an ideal solution. What's more, we're clearly very focused on kind of rigorous neutral research. Public goods really ought to be owned by the most aligned interests with the general public good. Many times private interests are misaligned with that. So we're aiming to serve as a kind of neutral territory to actually allow for well-aligned public good interests to come together and work on this whole research area. And then it's also worth mentioning that, when we're talking about a new piece of public infrastructure, one of the most fundamental aspects is standardization. A large part of what OpenCBDC is working to do is trying to figure out what those new open standards will look like, so that higher layers inevitably built on top of CBDC have solid expectations of what is necessary and what is possible. And then finally, it's worth mentioning that we're trying not to kind of pigeonhole ourselves to other things currently present in the space. This is not to say that blockchain technology isn't incredibly valuable and that there aren't incredibly useful things for us to learn from it. Only noting that centralized digital assets have very different requirements. In particular, the kind of scalability, privacy, and compliance concerns necessary for a CBDC don't necessarily mirror those of modern public blockchain. Okay, so that's why we went down this route. Let's take a brief moment. I'm just going to kind of walk you through a little bit more in depth what we've been doing this year and what we've released. So this winter, I mentioned in February, we released our initial body of work in the form of OpenCBDC-tx, which is a free and open source software repository on GitHub that includes 2 transaction processor architectures. And this was also released along with our full white paper that includes everything from security arguments down to the actual details of how the system is built and tested. We've released several other repositories since then, and we'll talk about some of them a little bit more in depth. But this spring, we began a couple of new CBDC research collaborations with the Bank of England and Bank of Canada. And of course, Project Hamilton under the Federal Reserve Bank of Boston is. And then finally, this last fall, we open sourced a couple of really large contributions to the various OpenCBDC projects. The first one, and maybe the most exciting one for some people, is three-phase commit, or 3PC, which is a new architecture, a third architecture, that enables programmability via really arbitrary stateful execution. I'll talk about all of these more in depth, by the way, so don't worry if this feels slightly quick. We also open source 2 tamper detection solutions. Both of them enable some level of auditability of the monetary supply, and one of them actually dramatically increases privacy of end users at the same time. And then the third thing, fairly recently, we just released a demo browser-based wallet, so you can see what it might look like to interact with one of these things as an actual user. And that actually includes a supporting Node.js module for programmers to interact programmatically with OpenCBDC to run in instance. That's kind of the general highlights of what we've done this year. There's been a really busy year, actually. I mean, we have a lot on the horizon, too. I'm going to walk through now a couple of the findings that we had from our original work And then I'll walk through a little bit more in depth some of what we just covered, what I just kind of briefly mentioned, and what we've been working on in the last couple of seasons. And I'll finish up with where we're headed, and then a bit of a live demo. So in our initial body of work, I mentioned we had two transaction processor architectures. The first one on the left-hand side of the screen was the atomizer architecture, and the second one on the right-hand side of the screen was 2PDC, which is a modified version of two-phase thing. I'm not going to go through the architectures in depth right now. For that, I would strongly recommend reading the white paper or taking a look at the technical webinar we hosted in March. But I will take a brief moment and talk about these set of components, the atomizer in the atomizer architecture and the coordinators. So in the atomizer architecture on the left, as transactions go through the system, eventually all transactions go through this single component, the atomizer. The atomizer then materializes a linear order of all transactions, so that there's actually every single transaction in the system has a happens before and happens after relationship with every other transaction. And that becomes very important for performance later on. So then talking about 2PC and the coordinators, this is in some ways the fundamental difference between the two architectures. Unlike the atomizer architecture, where there's a single atomizer and every transaction has to go through it, in 2PC, we can run multiple transaction coordinators in parallel. Doing this means we can't materialize that same linear global ordering, but it does mean that for any two transactions or any set of transactions which are independent, we can process them in parallel, which has significant performance. That's kind of the core of what I wanted to cover, because that's going to be important for the findings that we actually published and the slide I'm going to talk about. But I wanted to just mention again, there will be a Q&A section at the end. If you have any questions on any of the technical details, please feel free to reach out. We can cover them in more detail. Okay, so let's talk about the findings that we actually released in February. So the first thing, we were able to create a secure transaction format and data. And by that, I mean every transaction has truly cryptographic authorization to send. So once you as the transaction processor see a transaction come in, you know that transaction could only have been built by someone who has the required private keys to send those funds. Second, we dramatically minimize data retention. So the monetary supply in our body of work really takes the form of just a set of opaque hashes. There's really no data stored beyond that. So for example, we don't store the values associated to each input or output. We don't store the transaction graph. So we don't store who sent how much to whom and when. That is not recorded by the system. We really kept it as minimal as possible. And we did that for two reasons. The first is that it is incredibly positive for privacy, and we will talk more about that later. But it's also really important for performance. Just sending and storing less data makes it much easier to go faster. We also managed to have this transaction format be non-malleable, which is to say, once you have built the transaction, there's no way for anyone to modify it in a way that would be unacceptable. And two, they're non-replayable. So if someone is eavesdropping on you talking to the transaction processor and they see you actually send a transaction, there's no way for them to resend that same transaction and have you be charged twice. Okay, and then let's talk about the findings that probably made the most rounds. I mentioned there were two architectures here. Let's talk about, and that there were performance implications between their differences. Let's really kind of talk about that. So the first architecture, the atomizer, capable of creating this total linear order, really kind of capped out pretty quickly at about 170,000 transactions per second. And we know that you can probably make it a little faster. There are still some optimizations that you can probably apply. You can make this a little better. But at the end of the day, you have a single component that has to see every transaction in the system. There is a fundamental bottleneck. So the 2PC architecture trades off having that linear order for having almost complete parallel processing. The result is that the architecture scales somewhat linearly. As we add more machines, it's capable for processing more transactions per second. So we were able to demonstrate up to 1.7 million transactions per second, literally 10 times the performance of the atom. But it's worth mentioning, we actually have no real reason to believe that this trend stops. So if for whatever reason, a deployment of the 2PC architecture needed to support a greater throughput, it should actually be possible to scale up more machines, pay slightly more in infrastructure, and have a higher throughput. For our purposes, there was kind of only so much it made sense to pay AWS just to see a line. But that linear scalability is the biggest benefit of the 2PC architecture. And I want to take a brief moment and I want to step back and just kind of talk about what that looks like compared to some of the modern payment networks that we use every day. So Visa, one of the largest payment processors in the world right now, really does about 24,000 transactions per second. PayPal can do about 193, and Bitcoin's really about 7. So even the atomizer architecture itself far outstrips all of the modern payment networks that are available to us today. And the 2PC architecture allows for linear scalability out to almost any throughput you can imagine needing, assuming you're capable of supporting that level of infrastructure. So again, nearly 30 times faster, potentially more than a lot of the payment systems that we have available to us today. Okay, so that was our original body of work. Again, I've elided a lot of details like the security argument or the actual flow of transactions through the system. I just want to cover maybe the most salient points and then move on to where we're headed. So you can kind of see at the top, our research initially focused on these high performance processing architectures. And we've quickly moved into focusing on privacy and compliance and programmability. So I'm going to talk a little bit about those next. And then I want to talk about the directions that we're heading after we kind of tie more of a bow on programmability and programmability and privacy. And those areas that we're heading to are interoperability and offline. So first, let's talk about privacy. So our main goal for the privacy work stream up to now has been to look at privacy enabling temperature. In particular, in our initial body of work, if an attacker were capable of compromising any internal component in the system, they would be able to arbitrarily inflate or deflate the monetary supply, something that's effectively unacceptable in any production CBDC. More than that, depending on the component they manage to compromise, they might actually be able to live steal funds from people transacting with this. So we want to prevent these things. So as we began the tamper detection work, we took the initial threat model of, let's assume the attacker can compromise any single component in the system. So we need to prevent two things, or at least detect two things. First, we want to make sure if they actually do fluctuate the value in the monetary supply, we can detect that. It should at least be detectable. That's like the first step towards really preventing tampering. To try and do this, we explored two solutions for how you might detect any attacker fluctuating the monetary supply. The first one's maybe the most obvious. So in our original work, we didn't store any values. We only stored opaque hashes of funds. But if you just store values in the system, then you can run an audit where you sum up all the values currently in the monetary supply and see if it's what you expect. That's very effective and completely functional, but it reveals a bunch of additional data to the transaction process. And we know from experience that just the values in a transaction reveals a lot of personally identifying information. So we really didn't want to go too far down this road. So we took a second approach, which is implementing confidential transactions. Confidential transactions are a construction that instead of declaring that your inputs are of a particular value inside a transaction, you construct cryptographic proofs guaranteeing that the transaction is balanced. Then it turns out the transaction processor can actually just store a subset of those proofs. And come later when it's time to run an audit, you can do almost exactly the same thing as if you had stored the value, and more or less add up the cryptographic proofs and verify that it has the same balance as what you expect. That all works and is functional, but it has an additional benefit. Again, in the original body of work, the edge component that initially receives transactions from users, called the Sentinel, sees all the values in the transaction. It then compacts the transaction and sends the kind of compact transaction, which doesn't have the values, into the core transaction processor. With confidential transactions implemented, this is no longer necessary. The Sentinel doesn't actually have to see the values at all. So through this implementation, we've actually dramatically improved privacy. The entire transaction processor now no longer sees the values inside of a transaction, but has all the same auditability here. We can still run the complete audit with really the same level of effect as storing values. So that worked very well. Both of these are still undergoing testing to figure out their performance implications, which is why they haven't officially been merged into the repository yet. But both designs are open source and available to review. So the second thing we wanted to do, of course, we want to prevent theft of funds. Making sure that no one can artificially inflate or deflate the monetary supply is incredibly important. We also want to make sure no one can actually just take your money outside of the transaction. It actually turns out this is pretty easy to do. So the short version is that edge component, the Sentinels, you just give them a cryptographic key pair. And when they perform that compaction, they attest to the validation. They attest that that transaction is valid and balanced. And they sign off with their key pair as that attestation. Then to meet our threat model, we actually only have to require 2 of these attestations. Every component inside the transaction processor verifies these same attestations and makes sure that the right number was supplied. Doing so completely prevents theft of funds. So in this body of work, we've managed to both detect any fluctuation of the monetary supply and do so in a way that actually enables additional privacy of end users and prevent all theft of funds in the system, at least up to the specified threshold. That's kind of where we've been heading on the privacy. The next place we've been going, and maybe one of the most exciting places for I know a lot of people in this space, is really programmability. So this is taking the form of a new architecture. I briefly mentioned this a little while ago, called 3PC, or 3-phase. It is in some sense kind of a spiritual successor to 2-phase commit, but it really looks quite a bit different. So I wouldn't walk into reviewing that code expecting it to look exactly the same. 3PC more or less is kind of a distributed key value store, which allows you to hook an arbitrary virtual machine into it. This allows you to really do full distributed stateful execution of whichever virtual machine you've ported. And so far, mostly for demonstration purposes and admittedly on testing purposes, we've ported 2 virtual machines. The first one I imagine you've heard of, it's called the Ethereum virtual machine. And so far, our testing has been somewhat minimal. This is a very wide space. You're now talking about Turing-complete computing. But so far, we've tested both native transfers, so essentially transferring Ethereum in the Ethereum VM running on top of 3PC, and ERC20 token transfer. So if you were to issue a token, for example, a stablecoin, on top of the EVM, on top of 3PC, we've tested that interaction. We have some more tests undergoing on that architecture before it'll be fully merged, but that is on the way. The second virtual machine we've ported so far you might not have heard of, but it's actually surprisingly common out there in the world. It's called Lua. Lua is a general purpose programming language. It's very frequently used to write plugins for video games or other kind of plugin software. And you can really write anything on top of this. So you can write general software that would execute in a distributed fashion on 3PC. For our purposes of testing, because we are focused on digital currency and particularly CBDCs, we built a really minimal account balance structure on top of the Lua virtual machine. We have tested native transfers in that sense. That's where we've gone in the programmability workstream. First mentioning, this is actually still early days. There are a lot of other things to explore and how you might accomplish them. It's a whole open field out there. Okay, so that's what we've been working on for the last little while. Let's now talk about where we're headed. The first place, maybe one of the most important, is really about interoperability. This means a lot of different things to a lot of different people, but you can imagine this is incredibly beneficial, if only because it would improve remittances and cross-border payments. Cross-border payments are one of the weirdest payment workflows we have in modern society. Settlement finality can take place between 3 days and up to 3 weeks, depending on where the sender and receiver are actually located. And there's a lot of uncertainty about whether or not the payment will actually get to where it needs to go. So you can imagine by removing some of this uncertainty and reducing the friction in the system, you can actually enable users to just lead better lives and have better experiences with how they interact and transfer value to their friends, coworkers, and loved ones. You can also imagine, I mentioned interoperability means many different things to many different people. So what do I mean when I say interoperability? You might imagine that this is, between CBDC, right? Between like digital euros and digital yuan or something. You could also mean connecting a CBDC to current financial instruments like stocks, bonds, or cash. So for example, ATMs. You can also imagine how it might connect with other payment systems like SWIFT or POS. And finally, of course, this is a little bit more on the bleeding edge, but how it might interact with other digital assets. So like maybe bridges to Ethereum or some way of swapping atomic swaps. So far, our current plans for interoperability have focused on the top note of the notion of, let's just start simple and say we have two people who are holders of different CBDCs. How can we build a method for them to atomically swap their currencies without necessarily having to go through an exchange? And that work is coming up on the horizon. And we do have a breakout session on this, so please feel free to dig into that a little bit further. The second thing, and really another really fundamental aspect of CBDCs, is offline payments. This is one of the most important aspects for financial inclusion. As soon as you include a requirement for someone to be online in order to just send money to someone, you've dramatically raised the barriers necessary for people to actually use the system. But beyond financial inclusion, you can also imagine this has significant benefits for the system itself. The availability of the system, in some sense, matters less if you can transact even while the system is down or unavailable. That gives much better robustness guarantee. And furthermore, you can even imagine that the system is capable of being more efficient. If you don't need to send messages to one transaction processor every time you want to send money, that transaction processor can process fewer messages at a time and probably run faster, and therefore serve more transactions per second. And then maybe the most beneficial aspect of this, or at least one that's most compelling to me, you might actually be able to create something like real cash-like privacy, something that really more or less respects the freedom of the users engaging with the system. So there are a bunch of different ways you might imagine it implementing offline payments. There's one design that's somewhat well known so far, which is the use of so-called trusted execution environments. These largely take the form of things like ARM Trust Zone or Intel SQ. At a very high level, how this works, you can imagine that these trusted execution environments could guarantee key erasure. So for example, if I create a transaction that you and I are both offline, and this transaction gives you a new UTXO, a new bill for you to use, then the trusted execution environment can guarantee the private key I use to send my funds is deleted, so that I'm no longer capable of creating another transaction that would double spend those same funds. This isn't necessarily the only design out there, and it's not even necessarily the best design if there is a best design for offline payments. This is just one of the well-known ones that we are interested in. And it is worth mentioning then, if you have other ideas for how to implement offline payments, please talk to me. This is a space that we want to cover a variety of. So we've done kind of a lot of work in the privacy space, a lot of work focused on interoperability and financial inclusion, and we're headed in directions for interoperability and offline payments focused on financial inclusion and empowering users. Let's take a moment, and I'm going to actually just show you what it looks like to actually interact with this system. So I'm going to briefly give you a live demo. This is actually just running in a Docker container And this actually follows the README on our core transaction processor repository, OpenCBDC-tx. So right now you'll see we're just going to kind of set up a new wallet for Alice. And Alice is very fancy, so she gets to mint new currency. So we'll mint, let's say, 50 cents. And we can just double check that Alice indeed has 50 cents in the form of 10 5-cent UTXs. Alice needs someone to send money to, so let's make a wallet called Bob. And then we can send Bob, let's say, 30 cents. So we copy Bob's address, we paste it in, and we send it. And at this point, you can actually see at the bottom that the Sentinel has responded, the transaction is confirmed. At this point, Alice no longer has that money anymore, and Bob does. So we can go ahead and check Alice's wallet, and we can see that Alice indeed only has 20 cents, down to 4 UTX. Kind of an odd thing about how the transaction processors that we built works is that you need to communicate something out of band. So you can see Bob actually doesn't have the money in his wallet yet. It is worth mentioning the transaction processor is of the belief that the funds are now under Bob's control. This, you can see a line up there that says data for recipient import input. Bob needs to take that and put it in his wallet so that his wallet is aware of those funds. And then what's more, we'll double check this here. It doesn't show anything yet. Bob needs to tell his wallet to sync up. And now, ta-da, Bob has 30 cents. It is worth mentioning that all of the bottom 5 commands, so checking Bob's wallet for his balance, importing the input, syncing it, none of those talk to the transaction processor. All of that was essentially bookkeeping necessary for Bob to actually be able to send those funds. But the actual transaction processing happened as soon as Alice said so. Okay, that may not be the most compelling demo that you've ever seen, or the most exciting, but this is a live transaction that went through a real transaction processor. You're kind of getting all the benefits of QPC happening right now. And this is something you can run locally, both either, again, in Docker or just on your personal machine. Okay, so I'm going to hop back to the presentation. That was kind of the live demo, so you got to see a rough idea of what it actually looks like to interact with the system. Now, all of this has been, to be charitable, kind of mildly interesting. What we've been working on, where we planned to head, how you would interact with the system if you were to run it locally. But now I want to take a moment and kind of talk about something potentially more important. Why does this work actually matter? CBDC is because it serves as this new piece of public infrastructure and potentially a completely new toolkit for interacting with financial systems, has this odd property that it touches on really almost every aspect of our world, from kind of money and currency itself, to the intersection with technology, to society and how we actually organize society itself. This is truly an opportunity for a ground-up redesign of some of the most difficult aspects that we face today. And how we engage in these things is really kind of vital to address. And it can't just happen with us. We need other people, and we need people with different backgrounds and expertise. Whether that's people who are familiar with finance and familiar with financial regulation, people familiar with technology, particularly in computer science, and of course, everyone else. This is research that's going to impact everyone. Everyone has a vested interest in how this will work. And people from a huge number of backgrounds are going to be necessary to implement this, from theoretical computer science to finance, to law, to policy, to economics. All of us have a vested interest, and all of us can contribute something very meaningful. Hopefully that was at least a useful pitch on why this feels important. So let me now talk about how you can get involved. And there are plenty of ways to do so. So the first, maybe the most obvious, is technical contributions. You can help us design, develop, review, and really test new functionality. What is actually capable of being done in a CBDC. You can also, a lot of people talk about this as being less glamorous, but this is some of the most important work out there. Refactoring and improving the code that we have is one of the most important ways to help new people get involved and make it possible for new people to contribute. This is some of the most important things. And of course, there are a bunch of domains that CBDC touch that are kind of new fields in theoretical computer science. Cryptography is a reasonably young field, and distributed systems even more so. A lot of this is an interesting space for people to contribute. You can also imagine there are a bunch of other, like I mentioned, other research fields that we need help on. Offline payments is a really obvious example. If you're going to have something offline, at some point you're going to need something physical. That might take the form of phones or smart cards, but some hardware is going to be present. And that kind of secure technology and hardware supply chain is something the DCI doesn't have a lot of expertise in. We could use a lot of help here. Privacy is also always one that we can use help with. Cryptography, like I said, is a new field and a very evolving field. But how you apply cryptography to really improve the privacy of people interacting with the system while still making sure that it actually functions in the ways that it needs to function are a very open question. And of course, economics is kind of a fundamental aspect. You can also imagine economic incentives and how they help people behave well in the system or help to avoid attackers or malicious attacks. But the economics of what works best and what designs or what financial instruments could be built into a CBDC to enable great functionality are very much an open question. And then it's also worth mentioning, expert contributions don't only have to take the form of technical contributions or research. It's fair to say that there are a lot of aspects of this that are going to need policy. And whether that's having expertise and understanding for what current regulatory environments look like, or what the spirit of those regulations are, so that we can make sure it is feasible to meet some measure of that burden, are really necessary. And also knowing just the requirements of the system. What does the system actually need to do? You can also imagine third-party providers, like who will actually provide the wallets? What additional services might they offer? What would that actually look like, and what are the benefits for them to do so? These are definitely things we could use help answer. Now, I left it somewhat implied here, but let's make the subtext text. Who can actually contribute here? I would like to hear from genuinely everyone. In some sense, I'm kind of dyed in the wool on the free and open source side. So whether you're a central banker who has deep familiarity with the regulatory regime, but isn't super familiar with the technology, I would like to hear from you. Whether you're a student or a professor studying some of these things in this space, I would like to talk with you about this. If you're in the private sector and you think there's an aspect to this that your company could help leverage or help improve on and bring some of your expertise to the bear, particularly in some of the really prickly questions like the hardware supply chain or distributed systems, we definitely could use your help. And of course, like I said, this is public infrastructure. Everyone has a vested interest. If you're a hobbyist engineer, you are welcome here too. If you want to actually dive in, here's a nice URL for you to click on. We do have a quick start guide up on our GitHub, and that link will take you directly to the quick start guide. That guide is a subsection of our overall contribution guide. Hopefully that will answer most of your questions, but of course we have a Q&A session here coming up. And also, it's worth mentioning, we are always available if you'd like to reach out to us, I say offline, but how about asynchronous? At OpenCBDC@mit.edu. Please feel free to reach out. We're happy to answer questions. And then here's just some kind of useful resources for you to dig into. And this slide is going to be left up a little while later on, so you can copy down links. I know communicating URLs is not the easiest thing to do. But this will include links to everything from the GitHub repo to Zulip, which is where most of our online discussion happens, to our white paper, and of course, to our technical webinar. Okay.
Thanks, Sam. Thanks so much for your awesome presentation. We have a great set of questions here, and given the time constraint, we won't be able to get to all of them, but let me just pick out some that I think are really salient. So let's start with this question that's asking us to clarify what we mean by in our work in programmability. Question is, does using EVM mean that you implement CBDC on Ethereum?
Okay. That is a very reasonable question. No, it's in some sense kind of the reverse. So you can imagine 3PC operating as the underlying layer. And if a central bank wanted to deploy 3PC and, for example, use Ethereum, the Ethereum virtual machine, as their CBDC, they could do so and run it centrally. But really, the CBDC, more or less, is kind of operating at a lower layer. And for example, we haven't done this, but it should actually be possible to implement the original 2 transaction processor architectures on top of 3PC and have those operate as the kind of CBDC layer, with 3PC as just being the execution engine. And it's very, very worth mentioning, we're not trying to suggest that EVM is necessarily the one that would make sense to execute a CBDC on. This was more for demonstration and testing.
Great, Sam. Question on interoperability. Do you have some technical requirements to connect with your CBDC?
That's a great question. That's a really good question. So for the transaction processor architectures we've explored so far, no. More or less, you just need to be able to talk to the Sentinel. And that just requires an internet connection, hypothetically. But you can imagine there are kind of implicit requirements, right? So for example, just being able to talk to the Sentinel, that doesn't really do anything unless you can send the Sentinel a message that it understands. So the transaction format becomes an implicit requirement. So if you're thinking about interoperability between 2 CBDCs, you could imagine that taking the form of, well, if both of them are the same system, like let's pretend that both of these CBDCs actually were running 2PC, the interoperability question is mostly solved. You can just send your transaction to whichever Sentinel you're particularly interested in. If instead the 2 CBD systems have different underlying components, or their transaction format is different, you need some way of having compatibility, talk between the 2. That might take the form of a pretty minimal change to the system, exposing some additional functionality, for example, to be able to query if a transaction completed. Or it may require something much larger, for example, a direct connection between those 2 CBDCs worked out bilaterally. In many ways, that's kind of a question that we're still exploring.
So Sam, we have a couple of questions regarding the atomizer architecture, and they have to do with, hey, this looks awfully like a blockchain. Can you explain how the concepts relate?
Yeah, that's a really good question. So you can kind of imagine the atomizer architecture, in some sense, started from the notion of, could we build a high-performance centralized blockchain? And if you kind of squint and tilt your head a lot, atomizer does actually look a lot like a blockchain. Actually, if you read through the code, you can even see the atomizer actually publishes blocks. The blocks that the atomizer architecture publishes don't really look anything like blocks in, for example, cryptocurrencies like Bitcoin. Most obviously, the blocks don't have any fixed set of transaction size. The blocks can be any amount of size, and any size at all. That's a wildly different change. But in some sense, the similarities really stop there. The blocks don't really have any significant meaning in the atomizer architecture. There's no real reason you couldn't just completely elide the notion of blocks and have the atomizer publish single transactions. The only reason you probably wouldn't want to do that is for performance. So our blocks are, in some sense, just kind of a batch. But it is a fair insight to say that it does bear some resemblance to a centralized blockchain.
So we have an interesting question from the policy side.
Okay.
And data retention is minimized in the architectures, as you've explained, Sam, but can some components of the data transfer be activated by policymakers? And it's activated, I suppose it's, what is there room for policymakers to take part in this architecture? I think that's what the question is.
Yeah, I'll kind of answer that in two ways. So the first thing I would say is just from the kind of technical feasibility side, which is, we minimize data retention for kind of three reasons. And I mentioned two of them already in the presentation. The first one is that it's really important for privacy guarantees. Second is that it's really useful for performance. The third one is a little bit more conceptual. In some sense, it's kind of always easy to reveal more information. It's really hard to take information back once you've published. So we've kind of constrained ourselves to working really focused on minimizing the data in the system. But part of the benefit then is that for an actual implementer or policymaker, it's really easy to require additional information to be stored. There are just going to be some trade-offs that you make in that decision. So here's one example. Right now, even after the privacy enabling tamper detection work, where values are blinded, the Sentinel still sees the full transaction, right? The Sentinel has to know who sent money to whom. In our system, that is known only as public keys, so it's still pseudonymous. But that transaction graph is visible at the Sentinel link. It's not stored more internally, but it is present in part of the system. Some of our future work is actually going to look at what it might take to blind that transaction graph. But to talk about this hypothetical, you can imagine if someone needed the ability to enable some kind of data collection for some reason. I actually can't think of a good reason to do this, but let's pretend you had a good reason to do it. You could enable Sentinels to actually start recording a log of who sent money when. And after the privacy enabling tamper detection work, you wouldn't necessarily be able to know how much was sent, but you would be able to know who sent and when. And that could ostensibly be toggled on and off. From the policymaker side, there are plenty of places that it would make sense to plug into the system, whether that's taking part in the audit routine to actually verify that the monetary supply is balanced appropriately, or security audits of the system overall, or for example, third-party wallet providers, ensuring that those meet the requirements that are necessary for a wallet to actually serve users' needs. There are plenty of places that policymakers can absolutely.
Thanks, Sam. We have a question about so here it goes. I'm wondering how you design your test suites and test suites and harnesses with respect to ensuring correctness. Specifically, do you formally verify core aspects of your approaches? So it's a question about what kind of testing do we do, what kind of guarantees we might be providing to those who are looking at this code and potentially investigating this code base?
That is such a great question. No one at the DCI, to my knowledge, has a specific background in formal methods. I dabble with it, and I am very interested in the kinds of guarantees that you can make with formal proofs. Currently, the code present in OpenCBDC is not formally verified, and that's true top to bottom. We do have a strong security argument made by our kind of cryptographer in residence, Madar Zurka. But that security argument makes assumptions about the underlying cryptographic primitives. So the formal verification isn't going to be complete. It's also worth mentioning there's kind of one asterisk to put there that formal methods really can't solve all problems, particularly not problems with cryptography. They're really interesting. I will add one more answer to this question before I talk about what we actually do instead of what I would like us to do. I would love to enable more formal verification in OpenCBDC. I think that's an incredibly powerful benefit to us. So, contributions welcome. In terms of how we currently design our test suites, though, a lot of that is focused with ensuring that the behavior that we see kind of at the system level, so like, does a transaction actually go through the system the way we expect? Does the monetary supply remain balanced? that kind of thing largely drives our test code. So observability. Formal methods are definitely something I would like.
So Sam, I want to end with this question, which is, how can a developer get involved in helping develop the OpenCBDC codebase? And specifically, are there workstream meetings that are open for people to join?
Yeah, that's a great question. So we have hosted several working group meetings, and several large proposals were made in those working group meetings, namely focused on strong privacy guarantees and adding them to the system. We actually haven't hosted a working group meeting in a little while, partially due to some turnover in students. There's darn students graduating all the time, but also just because we wanted to get some of the work finished on some of those strong privacy guarantees before we kind of let proposals pile up. If you want to get involved in conversations or discussions, I'd strongly recommend diving into Stuewe. If for no other reason, because I idle there essentially all the time. So if you want to send me a message, it is a really easy way for you to get a message. We do have some plans to kind of restart some version of the working groups again. Hopefully one that's slightly less live and necessary for everyone to be on video so that it can be a little bit lower friction. But those plans haven't been finalized yet. Keep your ear to the ground. We will have that information available soon.
Well, thanks, Sam. I think this might be a good place to end the Q&A session.
We are really just going to wrap up. We're almost at the end, but we wanted to remind you about how to stay connected and get involved. And then lastly, share a kind of special invitation. So if you'll go to the next slide. Great, thank you. Oh, the one before it. Sorry, Sam. Thanks so much. Yeah, so I know we've shared these links, so hopefully they're ingrained in your memory. And if not, I think Christy will probably share them again. But I saw in a lot of the polls, you know, people say, how do I get started? What's the way to get started? That might be a block. We have done our best to really include the most clear kind of how-tos and guides and a lot of narrative content. So when you go to the GitHub, it's not just, you know, it's not just assuming you all are coders. It really is trying to walk you through all the best ways to start, how to have conversations with us. So I really encourage you to do that. And then of course, if it's more of an open form question, conversation in our group, I know we had a lot of people talking about research they're doing, which is fantastic, in different parts of the world and whole other dimensions than what we're tackling, and a curiosity to collaborate. So please email us. That's another way to get involved. And so again, just to reiterate, everything that Sam said, right, there's going to be a huge impact, and the value of that impact, whether positive or negative, is really up to us at this moment. And so we really feel that one of the best ways we can contribute to moving the structures of money and the systems of money into a more improved place is that we need to do research, and we need to do it rigorously and well, and we need to do it now while the systems are kind of starting to get set in place. So whether you're a programmer or a researcher or a central banker or a social scientist or a multi-billion-dollar company or a tiny startup or an individual who just cares about these topics and kind of where digital money is going to go, we really want to not just hear from you, but hopefully really meaningfully interact with your thoughts, ideas, suggestions, and questions, and ideally your contributions. As Sam said, this is open source project. And so the best thing is to actually get your hands dirty. That's a part of why we also started with so much hardcore technical research, is that the most powerful way to understand what's possible in the system is to actually start trying to build the system in different ways. So again, please find us on Zulip, as has been shared, and you can, at the top of our contribution guide through this link is a very short quick start guide. That's kind of the best place to go every time you forget how to get in touch. And we will see you in January, if you go to the next slide, for the next kind of public offering we have to share, which is actually about research we've been doing, also related to central bank digital currency, but combining our technical expertise with a group of social scientists and experts in kind of the sociology of money. And so we have done research in 4 countries, in Nigeria, in Mexico and Indonesia and India, all with local researchers in those countries, trying to evaluate which design choices within the CBD system might actually matter the most for users and the pain points they have with the current system. So please join us for that release. Free and open to the public. Invite anyone you want. You can get to it from our website, dci.mit.edu. You do need to register to join. And that'll be kind of another chance to interact with a different angle of this system. And for those of you who are excited about financial inclusion possibilities of this tech, a chance to hear where we see that possible and where we have questions. And without that, I will thank you all for joining, and we'll see you hopefully in the new year.